Hi folks, in this video we're going to have a look at what is meant by Kepler's third law of motion, and we're going to look at how we can apply that to calculations then along with gravitational fields. So with this question, part A is asking us to show that the mathematical form of Kepler's third law is consistent with Newton's law of universal gravitation. So let's start off with what is Kepler's third law. Kepler's third law states that the square of the period of revolution of the planets about the Sun is directly proportional to the cube of their mean distances from it. So what they're saying there is that t squared, t being the time period of the planets around the Sun, is directly proportional to their distances from the Sun, and we use r to denote that, and that is r cubed. So to verify that Kepler's third law is consistent with Newton's law of gravitation, we basically want to start off with Newton's equation, and we want to show that t squared is equal to some constant multiplied by r cubed. So when we are talking about planets in orbit around the Sun, they are moving in a circular path. So the planets in orbit around the Sun are taking a circular path, which means there must be a centripetal force. When it comes to planetary motion, it is gravity that provides the centripetal force. So our starting point to show that Kepler's third law is consistent, our starting point is to state that the centripetal force is provided by gravity, that the gravitational force is what keeps it moving in a circle. So gravitational force is equal, or is providing, the centripetal force. So what equation do we have for the gravitational force? We have that the capital letter G, which is the universal gravitational constant, multiplied by mass 1 times mass 2. In this case we're talking about the Sun and the Earth, so I'm going to use ms for the Sun and me for the Earth, divided by the separation squared. So the separation is how far from their centres they are separated. That gravitational force is equal to the centripetal force, and we do have an equation for the centripetal force. We would have met that earlier in the year, and that equation is mr omega squared. Now we're talking about the Earth orbiting around the Sun, so that is the mass of the Earth here that we're talking about. And actually at this point we can see that that term appears on both sides of the equation, so we can actually just cancel that out. What I want to do next is I want to get rid of that omega symbol there, which is the angular velocity. There is a link between angular velocity and time period, and that's how we're going to get t into this equation. So omega is equal to 2 pi f, f being the frequency, but since frequency is equal to 1 over t, we can also say that omega is equal to 2 pi over t. So I'm going to rewrite the equation, but instead of writing omega squared, we're going to put in 2 pi over t squared. So that's leaving us with g ms over r squared is equal to r times 2 pi all over t squared. Now the next step here would be to multiply out those brackets. I think I'm also going to bring up the r squared from the left hand side. It's on the bottom. I'm going to bring it over to the right hand side so that it becomes a multiply. So we have g ms is equal to r cubed multiplied by 4 pi squared over t squared. So nearly there. What we're going to do next, I'm just going to continue here off to the right. What I'm going to do next is I'm going to bring that t squared, because it's on the bottom line on the right hand side, I'm going to bring that over to the left where it will become a multiply. So we have t squared multiplied by g ms is equal to r cubed 4 pi squared. Now we're getting closer and closer to this statement that we wanted to end up with, that t squared is equal to some constant multiplied by r cubed. So the only thing left to do is I'm going to get rid of g and ms from the left hand side, bring it over to the right. So I can say that t squared is equal to 4 pi squared all over g ms multiplied by r cubed. So if we actually look a little bit closer at what we have here in the middle, we have 4, which is a number, so it's constant. We have pi, which again is just a number and is also constant. We have g, which is the universal gravitational constant. And then we have ms, which is the mass of the sun, which again for these equations it is approximately constant. So everything there circled in red is a constant. So we have shown that Newton's law of universal gravitation is consistent with Kepler's third law, because we have shown that t squared is equal to some constant multiplied by r cubed. Now we'll apply this equation then to a calculation. I'm just going to rewrite it here. So we have t squared is equal to 4 pi squared divided by g multiplied by ms times r cubed. So remember that when we came up with this equation, we had ms being the object in the middle, which was the sun, and then we had the earth orbiting on the outside of it. Now in this question part B, we have the earth has a mass of 5.98 by 10 to the 24 kilograms, and the distance between the centres of mass of the earth and the moon is 385 megameters. Show that the orbital period of the moon around the earth is around 27.5 days. So we're not talking about the earth going around the sun. Here we're talking about the moon going around the earth. So I'm just going to change the notation slightly of what we have written here. So we're going to get rid of sun. And we'll get rid of the earth. And we'll rename that so that we have the earth at the centre and the moon is in orbit around it, which means that the notation is going to change here in the equation, in that the mass of the sun is not at the centre, rather it is the mass of the earth. So we want to show that the time period is equal to 27.5 days. So our equation is already in the form of t equals, so now it's a matter of putting the values into that equation. We have 4 pi squared over g, which is 6.67 by 10 to the minus 11. That value is given to you on a data sheet. Multiplied by the mass of the earth, which coming from the question is 5.98 by 10 to the 24. And that's all multiplied by the distance between the two. And that distance is given as 385 megameters. So that's by 10 to the power of 6. And then don't forget that that distance is also cubed. So popping that into the calculator, what we find is that that is equal to 5.65 by 10 to the power of 12. But don't forget that's still t squared, so that's seconds squared. So our time period is the square root of that value. And that is equal to 2.37 by 10 to the power of 6 seconds. Now we need to convert that into days. So we'll divide that number first of all by 60 to convert it into minutes, divide it by 60 again to convert it into hours, and then divide by 24 to convert that into days, and that will give us 27.5 days. And that's exactly what the question had asked us to show. So hopefully you found that video useful.